Hello and welcome to this film, which is all about Ka and pH. Our infestation problem seems to have been solved, so we can go ahead and look at the connection between the things that we've learned about Ka and the things that we've learned about pH. And hopefully by the end of this film you'll be able to use a little bit of maths to convert between one and the other. So before we start doing any of that stuff, let's just remind ourselves of what an acid dissociation constant Ka tells us. Okay, so it gives us a measure of how much of our acid, Ha, reacts with water to produce the conjugate base of the acid and the conjugate acid of water, H3O+. So when it's large, it means that our acid is good at dissociating. When it's small, it means that not much of our acid dissociates. Now, let's say that we had a 1 mole per litre solution of ethanoic acid, right? This concentration tells us that in every litre of water we've dissolved 1 mole of ethanoic acid. However, hopefully you can see that if some of this acid, even if it's a very small amount, if some of it splits up into ions, then the concentration of HA at equilibrium will not be 1 mole per litre. It will be a bit less than that because some of it will have turned into these products. However, if we say that that amount is very small, so in other words hardly any of this dissociates, then basically we can assume, it's not quite true, but we can assume, and it's good enough, that the concentration of HA at equilibrium is the same as the concentration of HA that we start with. So that's an assumption that we can make, and it starts to make Ka a little bit simpler because we'll often be told the concentration of the acid that we have. What is more, and it's not really an assumption, it just has to be true, is that if HA splits up into ions, then we're always going to form 1A- for every H3O+. In other words, these two concentrations will always be the same as each other, and so we can basically end up with a slightly simplified version of Ka that says that this is equal to the concentration of H3O+ squared over the acid concentration. And you might remember that H3O+ is basically the same as H+, and so that this equals the concentration of H+ squared over the concentration of the acid. And now hopefully you can see, because pH is equal to the negative log of H+ ions, there is now a link between pH and Ka. Okay, and what we're going to do now is we're going to work through a couple of examples so we can see what that link is and how we can convert between one and the other. Okay, so let's start with this example, which deals with an unknown acid HX. We know its concentration and we know its pH. And we're going to try and find the value of Ka. Okay, so let's write an expression for Ka, and we're going to use our simplified form, which I've just gone through. I'm not going to go through it again. I'm just going to write it down and say that it's H+ squared over the concentration of HA. Now, the concentration of H+, if we know the pH, is simply equal to 10 to the minus pH, so it's 10 to the minus 4.5. And I've used my calculator to tell me that that is 3.16 times 10 to the minus 5. Okay, in which case Ka equals 3.16 times 10 to the minus 5 squared divided by this value here, the concentration of the acid, 0.4. Now hopefully you're not getting confused by the fact that I'm using HA and HX here. Remember, this is just the general acid. Here we're being told that the acid's anion basically is X minus. But anyway, I'll go ahead, I'll plug these numbers into my calculator, and hopefully I'm right in saying that that gives me the answer 2.5 times 10 to the minus 9. So the value of Ka for this acid is 2.5 times 10 to the minus 9. Now we're going to have a look at, I suppose, the reverse of that problem. So we are told Ka and the concentration of the acid, but we're going to try and calculate the pH of that acid. Now let's just write an expression for pH first. pH equals the negative log of the H+ ion concentration. And we also know that Ka equals the concentration of H+ squared over the concentration of the acid. So in other words, I can rearrange this expression hopefully to give me an expression for H+, because then I can find H+ and plug it into my expression for pH. So hopefully we can see that if Ka equals this squared over Ha, then the concentration of H+ is equal to the square root of Ka times the concentration of Ha. And that equals the square root of 1.7 times 10 to the minus 5 multiplied by 0.1. And without using my calculator actually here, I'm going to say that that's the square root of 1.7 times 10 to the minus 6. Okay, and definitely with my calculator now, I'm going to say that that is 1.3 times 10 to the minus 3. So the concentration of H+ ions is 1.3 times 10 to the minus 3. Put that into here. So pH is negative log of this, and we find that that's 2.88. Okay, so the pH of my 0.1 mole per litre solution of ethanoic acid is 2.88. And finally, we're going to have a look at a slightly different question, which is to do with the percentage ionization of an acid. Now, let's just stop and think about what on earth this might be telling me. Well, the percentage ionization is telling me what percent of the acid has ionized. In other words, what is the ratio of A minus to HA expressed as a percentage? Okay, so that's all I've got to find. I've got to find the concentration of A minus and divide it by the concentration of HA multiplied by 100%. But remember that the concentration of A minus is the same as the concentration of H plus. So in other words, I can say that the answer to my question is going to be given by this expression. Right, I've got the Ka. What can I do with Ka? Well, I can find the concentration of H+, because remember that if Ka equals the H+ ion concentration squared divided by HA, then the concentration of H+, as we showed on the previous slide, is equal to the square root of the Ka multiplied by HA. And in this case, the concentration of HA is 0.01, Ka is 3.72 times 10 to the minus 8, so this is the square root of 3.72 times 10 to the minus 10. And put that into our calculator, and we find that the concentration of H+ ions is equal to 1.93 times 10 to the minus 5. So now I know my concentration of H+ ions. I'm going to assume that the concentration of this at equilibrium is the same as it was at the start. And so, put this into here, divide that by 0.01, and I get 1.93 times 10 to the minus 3. Multiply that by 100, and I've got 1.93 times 10 to the minus 1, which is 0.193%. Okay, so there is a percentage ionization problem, which basically is a matter of finding H+, just like we did in the previous problem, but then working out a percentage, as in the concentration of A minus divided by the concentration of undissociated acid. So the amount that has dissociated divided by the amount that hasn't. All right, hopefully you've understood those different conversions that we've done. And you can now see a link between the things that we did on Ka and things that we did on pH. If you're confused about any of it, or if you've got any questions you'd like to ask or any comments you'd like to make, then please feel free to come and see me or to post a comment on YouTube.